Alright, this will start the combined lecture for chapters 32 and 33, starting off with electromagnetic waves. So, we've said that with Maxwell's equations we know everything that we need to know about electric fields and magnetic fields, and one thing that I noted was that Ampere's law said a changing electric field is going to produce a magnetic field, and also a changing magnetic field is going to produce an electric field. That was Faraday's law. What we as scientists have came to discover is we're going to have electromagnetic waves that are comprised of electric fields that are constantly changing. That's going to be propagating magnetic fields that are constantly changing. So what we're going to have is we're going to have an electric field that's along the y-plane that's going up and down, up and down, up and down, constantly changing. And that's going to be causing a magnetic field. That magnetic field is also going to be constantly changing. Here it's along the z-plane, and because it's changing, it's causing that electric field to constantly change. So essentially what we have here is going to be called a self-propagating wave. Now, the direction that the wave is going to travel is going to be perpendicular to both the electric field and the magnetic field. So here we have the electric field along the y-axis and the magnetic field along the z-axis, and so it's going to propagate along the x-axis right here. And how fast it's going to propagate has a special name. It's called the speed of light, c, and that's going to be equal to 3 times 10 to the 8th meters per second. So let's take a closer look here. These electric fields and magnetic fields, they're actually varying sinusoidally. So they're exhibiting wave-like behavior. Thinking back to chapter 15 and 16 when we talked about mechanical waves, we can express the electric field and the magnetic field in a very familiar format, where here we're expressing the electric field as a function of position and time in the j-hat direction. It's got some maximum amplitude. It's got a cosine kx minus omega t. Same with the magnetic field in the k-hat direction. One more thing that's going to relate these maximum amplitudes, fairly important concept, is going to be that the ratio of the electric field to the magnetic field must be equal to the speed of light. Now what's going to happen when these electromagnetic waves encounter different materials or encounter matter? Well, let's kind of conceptually look at a wave kind of coming into a transparent surface. Maybe it's glass or something like that. And we can say glass is made up of all these tiny little atoms right there with the positive nucleus and the electrons orbiting it. This wave is going to kind of get absorbed, or you can maybe even just kind of say gulped up by this atom right here. It's going to excite an electron, and then this guy is going to spit out that electron. It's going to be gulped up by this guy. It's going to excite an electron in this atom. It's going to pass it on to this guy, and this guy is going to get an electron that's excited, and then it's going to spit it out, and we're going to have a wave kind of leaving on the other side of this glass. It turns out that all that passing is going to change the speed of the wave as it passes through the material. Now, the speed of the wave is going to depend on the dielectric constant of the material, and we're going to have a dielectric constant for electricity and a dielectric constant for magnetism. So here we're kind of writing the speed relative to the speed of light and these dielectric constants. We can also kind of say that it's going to be related to the permeability and the permittivity of the material, but really it can be kind of cumbersome to remember the permeability and the permittivity. So we have a much easier definition where we talk about the index of refraction of a material, where this index of refraction is going to be the speed of light divided by the speed of the material. This number will always be larger than 1 because you can't be traveling faster than the speed of light. Much like mechanical waves, electromagnetic waves are also going to transmit energy, and when we talk about energy, we're going to be introducing a concept of a Poynting vector, which is really just going to be a power per unit area of the wave. Interesting thing is going to point in the direction of propagation, and we can kind of write it with this little s guy right here, where it's related to the cross product of the electric field and the magnetic field and the permeability or the permittivity of free space. you can kind of see conceptually here that here we have the electric field pointing up, the magnetic field is going to be perpendicular to it, so you cross those two guys, it's going to be pointed in this direction right there, which is also the direction of propagation. Now, how much energy is going to depend on kind of an energy density, which is going to be kind of an energy per unit volume. And then this little section right here is going to kind of represent a volume in space. It's going to be the area of the say laser beam, and then the CDT, which is going to be completing the volume. We can also talk about the intensity, which, if you remember, is going to be essentially a power per unit area, and that guy is going to be related to the pointing vector. Since the magnetic field and electric field are going to be sinusoidal, it's going to be related to their maximum values divided by 2. And we can also write it many other ways, so I'd highly recommend just kind of jotting those down because they might come up in a problem sometime. So let's take a quick look at example 32.4, where we're going to have a radio station. It's going to be transmitting average power of 50 watts. So here we got our 50 kilowatts. So here we got our transmitter, and it's essentially going to be transmitting equally in all directions above the ground, which is, as it says, very unlikely and very wasteful, up to a satellite. So perhaps that satellite can, beam that TV station to all of its other customers. And what we're interested in finding is the magnitudes of the electric field and the magnetic field by this satellite that's 100 kilometers away. So to do that, what we need to do is we need to figure out first what the intensity is. And to figure out the intensity is going to be power divided by area. So when you know what the power is, it tells us that's 50 kilowatts. To figure out the area, that's going to be one half of a sphere. So it's going to be 2 pi r squared, where r is simply the distance to the satellite. We calculate our area here. That allows us to calculate our power, and then we can relate the power to the pointing vector, which is also related to the maximum electric field. So now it's a simple matter of plugging it in, solving for the electric field, and then we can go ahead and solve for the magnetic field. I kind of like this example because it's kind of a almost practical real-life application, but also it kind of gives you a feeling for the magnitude of the electric field and the magnitude of the magnetic field for electromagnetic waves. Now, electromagnetic waves can also carry momentum, and therefore they can exert something called radiation pressure on a surface. We can kind of take a look at this radiation pressure. It's related to the pointing vector, which is a power. If we consider this guy right here, we kind of see this is going to be a dp dt, which is going to be a change in momentum. So that's going to be related to a force. Change in momentum is a force, and we divide that guy by an area, so we're going to have a pressure, and that's going to be related to the radiation pressure, or to the pointing vector, as well as the speed of light. So we can express that in terms of the electric and magnetic fields and kind of look at a flow rate of magnetic momentum. Kind of an example of a real life example of this is going to be satellites. We have satellites that have some solar panels that are going to catch the sun and power the satellite. And essentially, if the pointing vector or the radiation pressure is unequal on these two guys, suppose it's larger on this one than it is on this one, then this satellite is going to start to spin. And if it starts to spin, then essentially we need to burn some of our fuel. Fuel is a very limited resource for satellites, so we have a little sun sensor to keep equal amount of energy hitting both sides of this of the solar panels of the satellites. Now, another similarity between electromagnetic waves and mechanical waves is electromagnetic waves can be reflected, and they can be reflected by a conductor or dielectric. You can kind of think of an example of this would be, say, a mirror. A mirror is going to reflect light waves. This can also lead to standing waves, which we talked about for mechanical waves, where there's going to be regions of perfect interference and perfect constructive interference and perfect destructive interference. So here we have an electromagnetic wave incident on a perfect conductor, and it's reflected back in such a way that we're going to have constructive interference here, here, and here. This kind of leads to why we have turntables inside of microwaves. If you look at kind of a microwave cavity, there's going to be an electromagnetic wave in there, and so there's going to be hot spots, and then there's going to be spots where there's essentially no energy, and we want our food to cook evenly. Now this is actually a very super important slide, because it kind of shows the electromagnetic spectrum, which is going to be relating the frequencies and wavelengths of these electromagnetic waves. So let's just kind of quick little refresher on this. We'll just take a look at the electric field, and we're going to say we have an electromagnetic wave that's kind of propagating across the page right here. So the magnetic field would kind of be coming out at us. It would kind of look like that. We're going to define the wavelength the same exact way we did for mechanical waves, where it's going to be one complete cycle. And we also know there's a relationship for mechanical waves that's also going to apply to mechanical waves, where the speed is equal to the frequency multiplied by the wavelength. The speed is going to be the speed of light, so the speed of light is going to be the frequency multiplied by the wavelength. So here's kind of the spectrum in both wavelength and in frequencies of all electromagnetic waves. We're going to have radio waves, kind of microwaves, infrared waves, ultraviolet waves, X-rays, and gamma rays. And really kind of the definition, there's a little bit of overlap. It depends on kind of who you're talking to. You can kind of see that if you're looking in a region right here, some people may say it's infrared, and some people may say that it's microwave. Kind of same over here, and in this region right here. One very interesting tiny sliver right here is going to be this region from about 700 nanometers to about 400 nanometers, and this is going to be the spectrum of light that we can see. So it's really kind of humbling to think that there's all this huge spectrum running from 10 to the minus 13th all the way up to 10 of frequencies or of wavelengths that can constitute the electromagnetic spectrum. However, we're just sensitive with our naked eye to just a tiny little section right here. And you can kind of see the standard Roy G. Biv going across here from regions of low frequency to regions of high frequency, which is going to be regions of high wavelength to regions of low wavelength. So now let's talk about Chapter 33, which is the nature and propagation of light. It's going to be a long chapter, so I'm going to try to make it kind of speedy. We're going to talk about light rays and how we can talk about them as wavefronts. Important concept is going to be talking about reflection and refraction of light. Briefly mention total and internal reflection. Then we'll talk about the polarization of light. And lastly, we'll end with Huygens principle, after which I would highly recommend going back to take a look at reflection and refraction one more time, because it'll really help you understand those two concepts. So now let's talk a little bit about the nature of light. It turns out that light can behave like both a wave as well as a particle. So that leads us to the idea that there's going to be a wave-particle duality. Now, for this chapter, pretty much we're going to be talking about how electromagnetic waves are going to behave like waves. Essentially, if a wave is propagating, it's much easier to say that it's going to behave like a wave. If it's interacting with matter, which we'll talk about in a little bit, then it's going to behave more like a particle. So as we talk about the wave nature of propagating electromagnetic waves, we're going to kind of be talking about wavefronts as well as rays. Essentially, if we have a source, and say it's just talk about a mechanical wave for a second, like a ripple in a pond, if we were to throw a rock into a pond, then we're going to have kind of the crests coming out here. Those crests would be called wavefronts, and essentially in an electromagnetic sense, these would be regions of maximum electric field or maximum magnetic field. However, you can kind of see here that as you get further and further from the source, these wavefronts become kind of hard to draw. So what we do is we're going to draw what are called rays, and these rays are going to be perpendicular to the wavefront, and say, hey, this wavefront is traveling in this direction right here, this wavefront is traveling in this direction right here, and this wavefront is traveling in this direction right here. If we wanted to talk about waves that are planar, then we would say that these wavefronts are going to be just kind of like lines, kind of going right here, and then the rays are going to be perpendicular to them. So we're going to have electromagnetic waves that are traveling from the left side of the page to the right side of the page. That's going to also be kind of like the direction of the velocity. Now it turns out that number B here is going to be the more important one, and essentially if we say that we're very, 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 very far away from the source, then you can see here that these rays are going to look fairly similar to these rays right here. So we'll be dealing more with B than A here. So now let's use these wavefronts and rays to talk about two concepts of how electromagnetic waves can interact with matter, namely reflection and refraction. So here we have a lady whose hat just blew off, and you can kind of see her hat blowing away here. If she were to look over there, then she's going to, of course, see the hat outside of the window. However, as she looks in towards Alice's coffee shop, she's going to see an image of the hat. The gentleman on the inside, he's not going to see this image, reflected image of the hat. He's only going to see the hat outside of the window, and this is going to be a wave that is refracted. So we have some light waves that are coming from the hat, and we could draw the wavefronts kind of as such, and we would kind of draw them back like that. You can kind of see that drawing wavefronts is going to be rather annoying. So if we instead drew the waves, or the rays, kind of like this, and we kind of come up with this image shown here in part B, where we have the incident rays upon the glass. Here we have region A, that's the air outside, and region B is going to be the region of glass. And it turns out that these rays are all going to do kind of the same thing. So rather than draw kind of three rays that are reflected back towards the lady, or refracted or bent into the glass, we can just kind of simplify this down to just one single diagram, one single ray, because all those rays are going to behave the same. And what we can do is we can say we have some incident ray that's upon the glass coming from the hat. It's going to get reflected back towards the lady, so that's going to be the reflected ray. It's also going to get bent inwards by the glass, and it's going to be the refracted ray. And we're going to talk about all of these things, all of these angles relative to the normal or perpendicular line to the surface. So we can start to talk about this angle here, theta A, which is going to be the angle, since we're in material A, it's going to be that angle. We can talk about the reflected angle, that's just going to be theta sub r. And then we can talk about the light ray that is bent by the glass. It's inside of material B, so we're going to refer to that as theta B. And I'll talk about the relationship between these angles in a couple of slides. Now just a quick little side note on this idea of reflection. Turns out we can have two types of reflection. We're going to have specular reflection that's going to occur at a very smooth surface. For example, say a mirror, and in that case these incident rays are just going to all kind of reflect back in a nice pretty fashion. However, in the real world, there's something called diffuse reflection, which is going to occur on a very rough surface. So you can kind of imagine like a real surface having lots of nooks and crannies, and we can have the light kind of all coming in at the same direction and then reflecting at all sorts of weird different angles. This is a much more realistic scenario. However, we'll concern ourselves only with specular reflection. One real-life application of this, since I worked at NASA, is ground is going to reflect sunlight in a diffuse fashion, so it's going to reflect sunlight in all directions. So this satellite right here is just going to see light that's reflected towards it. In regions where there's lots of water, then we can actually have specular reflection, and we're going to, as the satellite kind of flies overhead like that, there's going to be a region where when it looks down it's just going to see a very bright image of the sun. You can kind of see this in this imagery right here. The satellite's kind of flying overhead and it's seeing this region right here where it's receiving a specular reflection from the sun. Rather annoying, because if you're trying to make measurements in that region, it's kind of hard with the sun shining directly in your eyes.